Howdy, everyone, and welcome to part two of our look at confidence intervals for proportion. This time we'll be looking at sample sizing, the other half of what we've done with most of our confidence intervals, with the exception of the t-distribution confidence intervals using t. And the reason for that is that if you're using t, you're really not concerned about sample size because the sample size is already dang small. So in the case of proportion, our sample sizes are generally quite large, actually, and we're going to see that today. Or we're going to see that in this particular lecture. So let's take a look back at the format of the confidence interval that you would have used for the last assignment, this one. So once again, the error, the 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 standard error that we're going to use, the error for our confidence interval, the range we go from our sample is always going to be the part that we're adding or subtracting from whatever our estimator is. So whatever we're adding and subtracting from p hat in this case. So that's going to be z sub alpha over 2 times the square root of p hat q hat over n. This part. So what we want to do is we want to figure out what the sample size should be. So once again, we're going to go ahead and try and isolate n. So let's take a look at how that happens. Let's just go ahead and try to isolate n in this case. So we go ahead and we'll start by saying that our error is supposed to be, wow, that was a terrible z. Not better, but we're going to roll with it. Our error is supposed to be z times p hat q hat over n in the square root, the z not in the root. So we're going to go ahead and try and isolate n. And our best way of doing that is to start by squaring everything, just to get rid of that root. So we get e squared equals z squared times, and now the root is gone, so we've just got p hat q hat over n. We can multiply both sides by n, and what we're going to get is n e squared, get there, equals z squared times p hat q hat. And now if we just divide both sides by e squared and then go ahead and combine the two squared terms together, we're going to get z squared p hat q hat over e squared. We can rewrite it like this. We can rewrite it as n equals p hat q. Whoa, that's a terrible hat. Well, I kind of lost control of my mouse there. P hat q hat times z over e squared. And this is going to be the equation that we use for our sample size. So this is the one you want. And you're going to see that in the slideshow. But this is what we want to be using. Once again, if we get a sample size, if we get a decimal answer, and we usually will, we're going to want to round up, always up, right? Because this represents a minimum sample size, and you can't sample a decimal number of data points. It's got to be a whole number. And if you round down, it won't be enough. So you have to always round up. Remember these little marks, right? The ceiling that we talked about in class, meaning round up. All right. So we're going to come back to this whiteboard in a moment, but for now, we'll go back to the slideshow. So let's get started by looking at the equation we want to use. So here, this is what we're looking at, right? We already saw that this is the error, and you just saw me isolate n. So we get n equals p hat q hat times z over e squared, z sub alpha over 2, obviously, over e squared. P hat and Q hat in this case, if we're trying to build a sample size to estimate a proportion, it's kind of weird that we need the proportion to estimate the proportion. So that's a little bit of a dependency problem. But the point here is that we're not using an answer to ask a question about what the answer will be. What we're going to use is we're going to use some past data if we have it. So if we have some assumption or educated guess or prior experiment that we can use to determine what we think p hat will be around, we can use that to figure out what our sample size would need to be, assuming p hat is somewhere near there. If we don't know that, we just assume the worst case scenario. P hat and Q hat will be at their, P hat times Q hat will be the largest when P and Q are both 5, or 0.5 rather. So if we don't know anything, or we want to play it safe, or we're just starting a new experiment completely fresh, or we're not basing off anything we've seen before, or we just want maximum rigor, we're going to assume that P hat and Q hat are 0.5. And that will mean that we guarantee that this is the largest possible n that achieves the confidence level and error that we want. So great. It's what's referred to as the maxi-min in what we generally use in statistics in something called game theory as well. It's essentially the maximum possible min value. And that's what we're finding here is the min, n represents a minimum value that achieves what we want, and the maxi-min is the most rigorous possible min. Not important for what we're dealing with right now, but mainly just focus on, if you have an assumption about what p hat and q hat are, you can use it. If you don't, use 0.5 for p hat and q hat both. Great. So let's go ahead and talk a little bit about what we're going to be dealing with in terms of examples. There's not really a lot here in terms of new formulas. This is it. So no big deal in terms of new material that you need to know. We just need to kind of see how to parse these problems. So here's kind of our example. And you might notice in this example that there's going to be a lot of percents, and that's somewhat unavoidable here. So I'll talk a little bit about how to parse this information. So let's take a look at this. You want to study the proportion of people who have heard of extreme ironing. At this point, I'm pretty sure everyone in this class has, because it was my background for a long time, and yeah. But anyway, you want to be accurate. You want to be accurate to a minimum, to a maximum error of 2.5% as part of a 90% confidence interval. What sample size is necessary if you have good reason to believe that about 20% of people know about this, or know about extreme ironing? So the issue here is there are 3 different percents. Nope, that's not what I want to do. One here, and one here. And they all are part of different things. This maximum error of 2.5% is E, and that's in percentage points. So that's not like a percent of the people that know. It's an error. It's a distance from some proportion. So it's going to be essentially our confidence interval is supposed to be at worst kind of plus or minus 0.025. 90% confidence interval, this is just telling you your level of confidence. And then 20% of people know about extreme ironing, or know about the greatest new extreme sport. This is telling you your assumption for what p hat might be. This is your starting assumption, your background information, your educated guess. So here, a lot of the key is going to be making sure that you assign the right information to the right variable, because we need p, and if we have p, we get q. We need p hat rather, and if we have p hat, we get q hat. We need z, and we need e. So z comes from the confidence level. E is going to be given to you in the problem. If you ever see the word error, maximum error, level of accuracy, saying like to within this much, saying something like accurate to within. All these are kind of catchphrases for the amount of error that you're willing to allow. And then lastly, if you're just saying, we expect the proportion to be, we have good reason to believe that about this proportion of people, right? These things are all kind of what p hat's going to be. And you can see here, I just straight up drew an arrow to show that this is going to, p hat. And if p hat's 0.2, q hat's 0.8. So here, this is a 90% confidence interval. 90% confidence in the Z table. We've seen this one a lot. Your big ones, as you've probably gotten used to at this point, are 90, 95, and 99. By the end of the year, some of you will just have these Z-scores memorized. We use them enough. So 90% confidence is a Z-score of about 1.645. We saw P hat and Q hat are 0.2 and 0.8 respectively. And then finally, our error is 0.025. So we'll turn our percent into a decimal, so 0.025. So we end up with 0.2 times 0.8 times 1.645 over 0.025 squared, all squared. If you calculate this out, it yields 692.74. So we round up to 693 and we're good. And this is what we need to do. This is it. This is the level of calculation you're going to have to do for tonight's assignment. Or for assignments involving this. There's really nothing more than just make sure you have the right information, and then it's one step of calculation. The issue I could see people having is mainly being sure, once again, to follow those order of operations, right? I talked about it in the last discussion, or the last lecture, and I'm going to talk about it here again. Is if you just type something into a standard issue just online calculator that's just 0.2 times 0.8 times 1.645 divided by 0.025 squared, or some kind of combination thereof, you're going to end up squaring everything, or you're going to end up not squaring the things you want to square, or something like that. And it might be hard to realize that happened because these numbers are all absurdly large, and squaring certain things really, you might not be able to detect that you've made a mistake. So I can just say, you really, if you have a nice calculator, you really want to type something that's, exactly this. Don't try and shortcut it. This is already written in simplest possible type for a calculator. There is no way to write it simpler other than to just, if you happen to know that 0.2 times 0.8 is 0.16, you could just jump to 0.16 right here, right away. But there's no real way to shorthand this other than doing some of the arithmetic ahead of time. But even then, you're not really shorthanding it. So if you're going to use if you're going to try and calculate things in one line, you really need to type exactly this. If you're not doing it in one line, if you're choosing to do this kind of by order of operations, do this part first, then square it, then multiply by 0.2 and 0.8. That is the only way that's going to work, because order of operations is a thing. Or I guess you could say 0.2 times 0.8 times 1.645 times 1.645 divided by 0.025 divided by 0.025. I mean, that works, but it seems unnecessary. So anyway, moving on. Just that was a reminder. Order of operations are a thing. Once again, sucks to get stuff wrong for reasons that you shouldn't. For mistakes you really shouldn't be making. So, just be careful, as always. And then let's take a look at this. You have no idea how many people actually know about extreme ironing. So here, if you have no prior assumptions, if you want to be as rigorous as possible, if we have any other sort of reservations about setting up a confidence interval, or you just want to have the broadest possible, or you want to have the most general possible answer, or you want to play it safe or whatever, just use 0.5 for P hat and Q hat. This is honestly what I would say most people would choose to do anyway, because again, it feels strange to look for p hat already knowing what you think it's going to be. That doesn't mean this doesn't happen. I mean, it happens all the freaking time. In fact, most times people do an experiment, it's confirming something they suspect. But all the same, if you're going to be rigorous, you shouldn't start with your answer. So maximum rigor, set, p hat and q hat to be 0.5. So n here is just, instead of 0.2 times 0.8, it's 0.5 times 0.5 times 1.645 over 0.025 squared. And here you can see that this number is noticeably larger than this one. Requires more sample, requires a larger sample size to guarantee that this is going to happen, to guarantee that the confidence interval you want is going to come about. So yeah, in this case, comes out to 1082.41, 1082.41. And once again, you need to round up. Even though this would normally round down, because it's sample sizing, you need to round up. So 1083. So let's take a look at one more example. Let's go with voting. Voting is kind of the most common way that we see confidence intervals for proportion come around. You have seen confidence intervals for proportion whenever you watch the news and anyone's talking about an election. They always say, well, we have this many people reporting in, and we expect that these are going to be the proportions to within, these are going to be the votes to within this margin of error. And that was confidence intervals. We talked about that in the last lecture. This time we're going to talk about setting up a confidence interval that you can be comfortable with. We're going to talk about how many people they need to survey to guarantee that they can actually make these statements. So here we're going for kind of maximum rigor here. So suppose a polling agency desires to show a projected proportion of voters to within plus or minus 1%. So this is what you generally see on the news. You will usually see, say, let's go with kind of current events. You might see, Joe Biden has 53% of the popular vote plus or minus 1%. That's pretty dang common. Most people like this plus or minus 1%. Because it feels accurate, but general enough that you're not like looking at weirdly specific numbers. So yeah, we'll go with that. So at least how many voters do they need to sample to be able to form this interval with 99% confidence? This is pretty remarkably confident. Not as confident as you'll see things happen. 99.5 gets used plenty. If you're going to be super accurate, you in one of the articles I had you guys read before the third quarter ended, we talked about kind of this level of understanding that was essentially something along the lines of 1 in 3 million. So 99 point, what 99997 or something in that respect, or something within, or well 67, but something close to that, which is pretty freaking remarkable. I might have had too many nines in there. 1 2 3 4, yeah, maybe, don't remember exactly what I said, but at any rate, 99.9 or 99% confidence is really as accurate as most people ever care to be. So here, once again, we want to be as rigorous as possible. So we're making no assumptions about p hat and q hat. So they should be taken to be 0.5. Especially with initial projections, this is pretty normal that you don't make assumptions. So here, the error is 1%. So E equals 0.01. For 99% confidence intervals, Z equals 2.576. We've seen this number plenty. A wonderful little thing I'll remind you is in the T table, we actually had the confidence in the T table. Yeah, even though this is for T, it actually has confidence level at the bottom and the Z score. So here, you could just go to 99 and look right there. There's your 2.576 for the z-score for 99% confidence. So that's a reminder that if I'm giving you one of the more common if I'm giving you one of the more common confidence levels, it's just right there in the t-table. So kind of pleasant. So let's look at what our answer is. So using, again, this equation, n equals p hat q hat times z over e squared, we just get 0.5 times 0.5, p hat q hat. Z is 2.576, and e is 0.01. So 2.576 over 0.01 squared times 0.5 times 0.5 gives 16,589.44, which we round up to 16,590. So this is a pretty dang remarkable sample size, right? This is huge. But that's perhaps to be expected. We're talking about being within 1% of the actual answer, where we're making no assumptions and trying to be 99% sure of our answer. It's to be expected that we need a huge sample size to accommodate that. So there's reason to say that proportions tend to have significantly larger samples than dealing with means. When you remember sample sizing for the mean, even when we tried to be hyper accurate, we were getting numbers that were in the low thousands, and here and even then, like, the low thousands was only when we were trying to be ridiculously accurate. Here, again, this is trying to be pretty dang accurate, but 16,590 is just huge. But when we're talking about trying to survey a population of voters, it's actually not particularly hard to sample this many people. I mean, that's just, a primary caucus. That's just not a problem, right? Or that's, with 2% of the voting population reporting in for a smaller area. That's really not that hard to accommodate. It's really not that hard to reach this for voting, which is why we do end up with these hyper accurate predictions once we actually start seeing voting happening. That's why usually you don't have to wait for states to complete reporting in. You can wait for like the first 5% of population to report in, and that's actually enough. More than enough, in fact. So yeah, let's take a look at a few more examples, and that'll cover what we want to do here. So I'm gonna move over to a whiteboard, and let's take a look at acceptance rates for a relatively new college. And I'm going to actually use a real college that was established about 20 years ago, no more than that. It's Olin College of Engineering. And it only recently kind of had a normalized acceptance rate. It only recently kind of had an acceptance rate that's kind of been confirmed by College Board, or not confirmed by College Board, but kind of like a generally accepted, like, oh yeah, no, this is how many students, this is what the proportion of students they accept. And the reason for that is that to kind of have an accurate prediction for their acceptance rate, it took time to collect enough data. So let's take a look at and that's a bit of an exaggeration. It wasn't that recently that that was fully accepted. It was probably 10 years ago, but still. So let's take a look at this. So here, let's say that we want a 95% confidence level. Actually, you know what? This supports text. We're going to try and write here. So we want a 95, let's say we want a 95% confidence level. And let's say that we want an error of, let's say, 1.5 percentage points. And let's say that we expect a 12% acceptance rate. Turns out I can't type and talk at the same time. So we might expect a 12% acceptance rate because there are other similar colleges out there that have this acceptance rate. So it might be reasonable to expect that. So we don't just have to start completely fresh. This is an example of where we have a good idea of an educated guess we can make. So here, out of this 95% confidence level, we are going to get a z-score of, let's make that a better z. We're going to get a z-score of 1.9. I really do suck at writing with a mouse. We're going to get a z-score of 1.96, an error of 1.5 percentage points. That's just the same as me saying that E is equal to 0.015. The decimal there. That is, let's make that look nicer. There we go. And then finally, 12% acceptance rate. That means we know what p hat is ahead of time, or we have a hunch at least. We have our estimation for p hat ahead of time. We don't know exactly what it's going to be, but we can make a good guess. And if p hat is 0.12, then q hat, we're gonna make that q hat is going to be, and now we're back to needing to write 8s. For whatever reason, that's impossible with a mouse. We're going to get back to q hat equals 0.88. So here, if we're looking at what n needs to be, we're just going to kind of say, well, n needs to be p hat, so 0.12, times q hat. Let's make that look more like a parenthesis. That's the best date I've ever drawn with a mouse. And then this is going to have to be times RZ, so 1.96 over RE, which is going to be 0.015. That is a very fat 5. And this bit is going to be squared. That looks a lot like a 9.5, so let's just make it a little more clearly. Let's make it a little more clearly a 0. Better. All right, so if we compute this out, again, we would do the 1.96 over 0.015 all squared first. That gives us about 17,073.78. And then we would multiply by 0.12 and 0.88. This ends up giving us about 1802.99. So the rounding here is pretty clear. Round up, which I think pretty much everyone would choose to do anyway. And we get an answer of 1803. So takes 1,803 people to reach this level of accuracy with 95% confidence, which is more than the applicant pool Olin has every year. So it took them a lot of years to be able to start predicting their acceptance rate. Not to mention that you have to wait for the college to kind of get, standardized as well before to kind of get a general idea of the people that apply as well. So it did take time. But yeah, that's kind of how this goes about. So let's take a look at one more example here. So this time, considering why it is that you're listening to a video lecture instead of actually in the classroom at BA, we'll go ahead and talk a little bit about, well, the coronavirus, because this is relevant. So one of the main things that various that the CDC or various governments or things like that are want to do is to estimate the proportion of people that are going to end up getting the coronavirus, given certain steps, given the steps that people take. So how a lot of projections are made, and quite correctly, is a lot of projections are made by looking at other places where the virus has already been, and looking for similar structures, looking for places that have similar structures to what your place is doing, for what your home is doing. So if you're not, if you're not really doing enough to contain the spread, or if people are still meeting, or people are still kind of going to public gathering places, then you might have to look at for with the benefit of hindsight, a few months from now, you might end up looking at, say, northern Italy. If you wanted to, if you had a place go into full lockdown, you might be looking at places like Korea, or maybe if it's more densely populated, Japan. But what you can do is you can look at places with similar structure, and there's always some inaccuracies here because different nations or cultures are going to have different biases, and it's always rather difficult to get a very precise answer, because you never know if something's going to swing what's happening. It's difficult to really make these predictions with just baseline statistics like this. You need kind of much more knowledge of the advanced mechanics going on, but we can start making guesses. We can start kind of building a frame. So here, what we might say is, let's say that we want, for whatever reason, a 98% confidence interval. We want to have whatever we're getting with 98% confidence, and let's say that we want a 2% error. So here we might just say like E equals 0.02. So 2 percentage points of error. And this time we're making no assumptions. So that means that P and Q are both going to have to be 0.5. So we're not going to make any assumptions about what P and Q are going to be. We're going to try and be, while we're going to sample a number of people coming from a similar place, we're not going to make assumptions until we actually see what their results are, because we don't know what their results are till we actually sample them. So we're just so yeah, let's take a look at what this generates. So 98% confidence. Let's start with that. 98% confidence essentially is something that's not in that I'm going to use here. It's not one of the most common confidence levels. The common ones, again, are 90, 95, and 99. So I'm going to start by just reminding you of how to find stranger levels of confidence. So let's kind of pop over to the Z table here. And I'm going to remind you that to find a 99% confidence level, we take that level of confidence and we subtract it from 1. So 1 minus 0.98. And so we get 1 minus 0.98 is 0.02. And then we divide that by 2, because we're looking for kind of an area only on one side. Remember that this table is for one side only. So we get 0.01, and we look for that in the table, which is right, somewhere in here, somewhere around negative 2.32 or 3. So that's going to be our z-scores. If we're going to estimate, probably negative 2.33. And then since, again, this is supposed to be just a general distance from the mean, we don't care about the negative. So we're going to call z 2.33. Now, admittedly, 98% is actually not all that uncommon. It is one of the confidence levels given in the t-table. So here we can see that what the t-table actually gives us is 2.326. So again, if the confidence level's in the t-table, just use it. If it's not, you need to do that whole 1 minus the confidence level over 2 and then look for that number in here. So yeah, we get 2.326, which, as we suspected, is somewhere between 2.32 and 2.33. So that's what we'll use, 2.326. Going back to the whiteboard, we get z is equal to 2.3. Whoa, that's terrible. There we go, 2.326. E already written out, 0.02. And then the no assumptions here tells us that p hat must be taken to be 0.5. And if p hat's 0.5, then so's q hat. So our sample size then is going to be p hat, which is 0.5, q hat, which is 0.5, and then our z, 2.326, over our error, which is 0.02. And this part, again, gets squared. So if we calculate that out, if you do 2.326 over 0.02, you're going to get 116.3. If you square that, you're going to get 13,525.69. I'm not writing this out because I think you can tell that I don't do particularly well writing on these whiteboards. But anyway, you get, if you deal with that, if you deal with, 2.326 over 0.02 squared, you get 13,525.69. And then you just multiply that by 0.5 by 0.5. And what you're going to get is you're going to get 3381.425. Let's make that a more obvious decimal. And again, here, this isn't good. This isn't good enough, right? This isn't a sample size. This is just an answer. This is just an answer to this particular computation. It's not a sample size yet, because a sample size needs to be I just realized I totally could have written this with text. A sample size needs to be a number, a whole number. So we round up to 3382, to 3,382. So if you're going to try and make a prediction about how many people are going to end up with coronavirus in an area, you need to survey a little over 3,000 people from a similar area to figure out what proportion of them ended up with the virus. And then you can make predictions about how your area will fare. And obviously these are very general predictions because there's just so many extra variables out there that it's just difficult to account for, or even impossible to account for, or just simply, the level of variance is going to be, difficult to predict, or difficult to account for. So still though, gives you a general baseline. So yeah, this is what's going on. This is kind of how to create sample sizes for finding confidence intervals for proportion, or confidence intervals rather, for a proportion. Again, this was not a particularly, not a low confidence level. 98 is pretty high. This is not a particularly accurate error. And we still ended up with over 3,000 for a sample size. So again, sample sizing for proportions tends to be quite large. So yeah, thanks, and until next time.